A patient arrives in the emergency department as a code stroke. Time is brain. The hospital's AI screening tool processes the incoming scan, analyzes the vessels, flagging no anomalies. The clinical team trusts the negative result and moves on. The patient, suffering from a subtle large vessel occlusion, misses the critical window for thrombolytic treatment. This catastrophic omission stems from a specific type of failure: systematic error. Random error is caused by unpredictable anomalies, like pixel noise. Predictions scatter without a distinct pattern, reducing precision without a consistent direction. Statistical bias creates reproducible misclassification of a fixed magnitude. The model outputs highly precise results that are consistently and predictably inaccurate. These mathematical deviations align with human cognitive bias to target specific demographics. An algorithm trained predominantly on images from white patients reliably underperforms on images from Black patients due to variables like increased breast density, quietly exacerbating existing health inequities. Bias functions as a compounding lifecycle pathology, infecting a model across 4 distinct stages of development. Tracing the mutation of bias from raw data curation to final deployment is the only way to audit clinical AI and prevent systemic patient harm. Data curation begins with the assumption that stripping explicit identifiers, like race or age, renders an algorithm fair. In reality, algorithms are built to find patterns, and they will find them in the most subtle proxies. This table illustrates DICOM metadata. DICOM is the standard communication protocol for medical imaging files. Even without explicit clinical labels, algorithms infer protected attributes from hidden metadata fields, like image type or patient sex. Latent variables remain within the pixel data. AI models predict racial identity directly from visual signatures, like varying tissue density or unremoved laterality markers. This leads to negative set bias, where training datasets overrepresent rare, severe pathologies. Sourcing data exclusively from specialized tertiary care centers trains the algorithm on an overwhelming volume of complex cases, leaving it unable to evaluate the real-world baseline of a typical community hospital. Further complicating the data is the reality of missing information due to human error or corrupted files. Engineers address these empty cells through imputation, the statistical practice of replacing missing data with calculated placeholder values. To plug these gaps, developers substitute missing variables with statistical averages derived from the surrounding data. By utilizing the mean or median of the entire global dataset, as seen here with the interpolated red 2s, engineers trigger data leakage. Data leakage occurs when information meant for testing contaminates the training set, allowing the model to train on shared characteristics of both datasets. Because the model previews test data patterns through these shared averages, its validation performance is falsely inflated. Training on artificially clean, contaminated data creates a mathematical trap. The algorithm produces exceptionally high validation scores while burying inherent clinical biases deep within its architecture. During model evaluation, relying on aggregate accuracy is a dangerous mistake. In medical AI, accuracy often functions as a deceptive metric that masks failure. Imagine 100 patients, 99 normal, 1 with pathology. An algorithm defaults to predicting normal for everyone, achieving 99% accuracy but diagnosing 0 sick patients. The F1 score, balancing precision and recall, penalizes ignoring the minority class. The algorithm's grade crashes to 0. Beyond metrics, evaluators must conduct rigorous subgroup analysis. Breaking down performance by specific demographic slices, such as age, race, and socioeconomic status, ensures the model functions equally across the entire patient population. Evaluating models using aggregate accuracy on imbalanced data mathematically validates underdiagnosis, ensuring the algorithm will fail the hospital's most vulnerable patients. The final stage is clinical deployment. Models leave the highly controlled training environment and enter the operational chaos of a hospital network. This graph illustrates the immediate drift that occurs in production. During testing, the orange learned function maps perfectly to the baseline training data. Once deployed, the underlying real-world data distribution begins to shift. This is covariant shift, a phenomenon where real-world input variables change, but the rigid mathematical relationship the model learned does not adapt. Operational changes trigger this shift. A hospital upgrades its software, purchases scanners from a new vendor, or alters its imaging protocols. As shown by the shifted test distribution, the algorithm processes these new, unfamiliar inputs using old rules, producing highly confident but completely erroneous clinical predictions. Because covariate shift occurs without throwing explicit software error codes, the failing model continues to operate, leading clinicians directly into a psychological trap. Modern reading rooms demand immense speed. Radiologists process hundreds of complex imaging studies in a single shift, creating an environment of peak cognitive load. This pressure triggers automation bias, the psychological tendency to favor an automated system's recommendation despite contrary evidence. Overworked clinicians commit commission errors, accepting an algorithm's incorrect output rather than trusting their own visual assessment. This flowchart maps a catastrophic chain reaction. A biased model is deployed. The clinician defers to its flawed output. This erroneous finding becomes ground truth. AI systems continuously update using historical data, meaning the model trains on its own mistakes, cementing bias into its architecture. Breaking this destructive feedback loop requires developers to abandon the goal of mathematical blindness. Ignoring demographic realities only replicates the flaws of the past. The solution is the deliberate integration of equitable bias. This involves intentionally oversampling underrepresented demographics and rare pathologies, applying corrective weights to force algorithmic parity. Objective fairness in clinical machine learning is a mathematical illusion. Preventing algorithms from automating our historical flaws requires us to engineer systems that value equitable outcomes over the replication of flawed historical data.